Okay, I'm going to go ahead and get started. So we're doing the 2021 exam today. Get started. So starting with nomenclature, again, nothing too different for the final exam. You'll still have your alcohols, triple bonds, double bonds, stereochemistry, all that kind of stuff. So for this first question, we have a cyclohexane in a chair conformation, and we have two alkyl groups. We don't have any double bonds or triple bonds, so for this one, it's going to be pretty straightforward. So before we can start numbering around our ring, you'll notice that our two groups are right next to each other. So if we were to number around the cyclohexane, you can number it in black, starting with one of the groups as 1, or you could number it in red like I'm doing right now. And so either way, our numbers would be 1 and 2. So to determine which one is going to get the lower number, we are going to use the alphabet, and the substituent with the lower alphabet letter is going to be the group that gets the first carbon. So the first thing that we'll actually have to do is we'll have to name our substituents. So just starting at the one on the top, we have a 1, 2, 3, 4, 5 carbon chain. So that would be a pentyl. And this 5 carbon chain has a methyl group coming off of carbon 2. So we're going to have 2 methyl pentyl. And since it's a complex sub, we'll put it in parentheses. And we'll just keep that off to the side for now until we can determine what number it's going to get. For the bottom substituent, again, same thing. We'll start numbering across the substituent. We get a 4 carbon chain, which will give us a butyl main name. This butyl group has 2 methyl groups coming off of carbon 3. So we're going to have 3,3-dimethyl butyl. And again, complex sub, so we put it in parentheses. So now to determine the alphabetical priority for these two substituents, we have to look at the lower alphabet. So remember that anytime we're looking at our alphabet, we do not consider number prefixes. So our number prefixes, would be di, tri, tetra, any of those. So we're going to ignore the number prefix that we have on the bottom substituent, and then we're just going to move on. So we have a methyl. In our substituent at the top, we also have a methyl, so we're going to have to go on further to what the main part of that substituent was. So on the bottom, we have a butyl, and on the top, we have a pentyl. So B comes before P in the alphabet, so this 3,3-dimethyl-butyl will get our carbon 1, and that means the other substituent is going to be carbon 2. So these are our two substituents. Again, our main parent chain is going to be this cyclohexane ring. So cyclohexane. And whenever we have a cyclohexane, we have to look at where the substituents are for stereochemistry. So whenever we have it in the chair conformation, we can look at the equatorial and axial positions or the up-down positions. So the 3,3-dimethylbutyl that we gave carbon 1 is on the down position at that carbon. At carbon 2, the pentyl substituent is also in the down position. So because both substituents are in the down position at their respective carbons, this one is going to be cis. So that's our stereochemistry. We don't have any double bonds or wedges and dashes to do E and Z or R and S. So we can just move on to putting our name together. So we have cis for our stereochemistry. We put our substituents in alphabetical order. So we're going to do 1, 3, 3-dimethylbutyl. And then our other substituent was 2,2-methylpentyl. and then our parent name was cyclohexane. So I ran out of room, so I'm just writing it below, but it would just be directly off of the parentheses. You wouldn't have a dash in between. So this is going to be our first nomenclature question. So moving on to question number 2. Here we have an alcohol, we have a triple bond, and we have a double bond. So our priority that we have learned in this semester, alcohol is going to get the highest priority. So since that's our prioritized functional group, we want to give that the lowest number possible. So we're going to start numbering from the left-hand side. And when we do that, we are going to get a 9-carbon chain. So our main chain is going to be non-ane. And then with the double bond, triple bond, and the alcohol, we're going to have to convert that into to reflect in our parent name. So we have non, and then for our double bond ene, it starts at carbon 7. So non-7-ene. Our triple bond started at carbon 2. So non-7-ene 2-ine. And then our alcohol was at carbon 4. So 4-all. So this is going to be our parent name. And then we move on to our substituents. So for our subs, we have a methyl group coming off of the carbon 4 on that dash. We have a methyl group on carbon 7 and a methyl group on carbon 8. So we have 4, 7, 8 trimethyl. And we don't have any other substituents. Remember, alcohol was our parent name, so that one's already reflected in the parent name. So now that we're done with our substituents, we move on to stereo. So for stereo, we don't assign any stereo for the triple bonds. We do have an alcohol at a chiral center and a double bond starting at carbon 7 that we'll have to look at for stereochemistry. So starting with the double bond on the far right of the structure, if we cut that molecule down the middle of that double bond, if you look to the right side, you'll notice that both of the groups on the right are methyl groups. And so whenever we have the same group coming off of that same side, we can't assign a priority between them because they're the same group. So because of that, we will not have E and Z for this double bond. So the last thing to consider is the chiral center at carbon 4. So we're going to do R and S for this. So alcohol is going to get our highest priority because it is the highest number on the periodic table. Then we're going to look at each of the other groups attached to that chiral center. All of these are going to be carbon atoms. So now we have to look at what they're attached to. So the CH3 group is just attached to 3 hydrogens. Going down to the left, this triple bond, we are going to consider this as bonded to 3 carbons because it's triple bonded to this carbon here. Carbon 5, it's connected to a carbon going up and to the right on the structure, and it's got 2 hydrogens of its own. So this one we'll say is going to be CHH. So because the group going down and to the left is CCC, it's going to be our next highest priority. And then the group going down and to the right is going to be our 3rd highest priority. And lastly, that methyl group, it's only bonded to hydrogens, so it's going to be our lowest priority. So if we bring our numbers out to see more clearly and we do our rotation, so 1 to 2 to 3, this is going to be an S stereochemistry. And our lowest priority group is already on the dash, so we don't have to worry about flipping it. We're just going to say S is our stereochemistry. So we've got our stereochemistry, we've got our subs, and we've got our main chain. So now all we have to do is put this all together. So out at the front of the molecule, we just have the one stereochemistry to consider, so we'll just put S. You don't need to put the number. Then we have our substituents, which were the 3 methyl groups. So 4,7,8 trimethyl. And then we have our parent name. We have non-7-ene 2-ine 4-all. So remember that for a parent name, the order is going to be ene, ine, and then all. So make sure you keep it in that order. And that's going to be our nomenclature for that question. So moving on to our last nomenclature for this exam, we have this long carbon chain. We've got a bunch of double bonds in there. So we want to give the double bonds the lowest numbers possible. And we also want to get the longest chain possible. So I'm just going to start numbering from the left to the right. We can see that if we go along this chain at the bottom, we're going to get a pretty long chain. And then just for good measure, I'm going to number backwards as well, because this one's a little bit trickier to see, so I want to make sure that I get the right numbers. So if we go across in black, going from left to right, we'll get our double bond starting at carbon 1. We have another double bond starting at carbon 5, and we have another double bond on that main chain at carbon 9. And then we have a substituent at carbon 5. If we number in the red, our double bonds are going to be at carbons 1, 5, and 9. And our substituent would be at carbon 6. So all of the double bonds would be on the same numbers, regardless if we went from left to right or right to left. But the difference that we see is between the substituent. So because the substituent in the black numbering is lower, we're going to go with the black numbering for this nomenclature question. So again, starting with the parent chain, we have a 10 carbon chain, which would be a decane. And then with the 3 double bonds that we have in that structure, this is going to become a decatriene. So deca, and then our numbers were 1, 5, and 9. 1, 5, 9, triene. Or if you like, you can put them at the beginning of the structure. So 159 decatriene. And that would be our parent name. So for our substituents, the only substituent we have is coming off of carbon 5. So we always number our substituents starting from the carbon they're attached to the main chain. So we get a 3 carbon chain, which would be a propyl. And then it has a double bond starting at carbon 2. So this one is going to become 2-propenenyl. And that substituent is on carbon 5 of the main chain. So we throw that out in front to show where that complex substituent is on the structure. So those are all our substituents. Now we just have to move on to stereochemistry. So we don't have any wedges or dashes, so we're not going to do R and S, but we do have a bunch of double bonds. So we'll have to evaluate each one and see if we have any E and Z. So again, like we saw in question 2, this double bond on the far left of the structure, the left-hand side is just going to be 2 hydrogens. So we can't assign a difference between those two. So this one will not have E and Z. And similarly, the propenenyl coming off of the main chain, we can't assign any priority between these. And at carbon 9, we can't assign any priority between those. And that just leaves us with this double bond starting at carbon 5. So at carbon 5, on the right-hand side, we have a hydrogen, and then we have a carbon chain going towards the top right. So carbon is obviously going to be a higher priority than hydrogen. So we'll put our star on that side. Then between the two carbons on the left side, so carbon one of the substituent coming off of the main chain, it's going to be connected to a carbon, and it's got two hydrogens, so we'll assign that as CHH. If we look at carbon 4 of the main chain, you'll also notice this one is going to be CHH. So because there's not a difference here, we have to move on to the next carbon. So we'll look at 3 of the main chain and 2 of the substituent chain. So at carbon 3 of the main chain, again, we have just a CH2 group, so it's going to be connected to a C, and then HH. Carbon 2 of the substituent chain up here, it's double bonded to a carbon, so we'll consider this as C, and then H. So because the substituent has this higher priority, we're going to consider that, we're going to give that one our star. And so you'll see that our stars end up on the same side of that double bond. They're both on this up position here. So this one is going to be Z. And again, we already looked at the other double bonds. We didn't have any E or Z for any of those. We don't have any wedges or dashes. So for this one, the stereochemistry is just going to be at that one double bond. So you can throw all of this together. Our stereochemistry is Z. Our substituent was 5,2-propenyl. And then our main name was deca 1,5,9-triene. Any questions on any of these nomenclature? Okay. Moving on to our facts questions. So again, with the final, we're going to look at some facts questions from exam 2, exam 1. So make sure you're going back and reviewing all of that stuff. I suggest looking at what you might have missed for your previous exams, kind of using that to learn from. So for this first question we're looking at, we're asked to look at a reaction rate with H2O. And you'll notice that we have a bunch of halides here. So for this one, we have H2O, which is a weak nucleophile. If you look at all of these halides, you'll notice that they are secondary. So because we have secondary halides with a weak nucleophile, we're going to say this is going to be an SN1 reaction. And so remember that for SN1, the first step, the leaving group leaves and we form a carbocation. So whenever we form a carbocation, we just put a plus charge at the position that that halide was. I'm going to cross out the halide and pretend we got rid of it. So those would be our carbocations for these structures. And for an SN1 reaction, the faster rate is going to be when we have a more stable carbocation. So for SN1, and for carbocation stability, it's going to be tertiary is the most stable, then secondary, and then much, much less stable would be primary or vinylic carbocations. Remember, a vinylic carbocation is one that's directly on a double bonded carbon. Now, when we look at all of these carbocations, you'll see in this first structure, we have a couple of double bonds adjacent to it. In the middle, we have one double bond adjacent to our carbocation. And on the far right structure, you'll notice that we have a vinylic halide here. So we know vinylic halides are going to be vinylic carbocations are going to be very unstable. And so because of this, we're going to assign this vinylic carbocation as our slowest rate. So then between the groups on the left and in the middle, this is going to come down to resonance. Both of them are secondary. They do have resonance structures, but the one on the left, we have 2 double bonds that we could resonate with, whereas the one in the middle, we only have 1 double bond that we could resonate with. So because this one has 2 additional resonance structures, resonance makes that carbocation more stable. So we're going to assign the group on the left as our most stable and therefore fastest rate, and the group in the middle would be our second. Questions on this one? Okay. Next question. Hydrogen atoms in order of increasing acidity. So whenever we're looking at acidity, we want to follow our cardio rules. So charge, atom, resonance, dipole induction, and orbital. And our first step for these types of questions is we want to form the anion. So we want to deprotonate these hydrogens and form a minus charge. So I'm just going to, again, get rid of the hydrogen and pretend we formed a minus charge at that atom. So now we have our 3 anions. The anion on the left, we have an O minus. In the middle, we have a C minus. And on the right, we have another C minus. So for acidity, we want the most stable anion. And to do that, we want either resonance, we want a more electronegative atom, or we want like induction effects or the orbitals. But for the purpose of this question, we only need to look at resonance and more electronegative atoms. Again, you'll notice that we have O minus, C minus, and C minus. So O minus is going to be a more electronegative atom because electronegativity increases going up and to the left of the periodic table. Sorry, up and to the right of the periodic table. And then in addition to the oxygen being our negative charge over here, we can also resonate this negative charge with this adjacent carbonyl. And we can form a resonance structure that also has the minus charge on oxygen. The group in the middle, we have a carbanion, and it's next to a double bond. So we can resonate this double bond with that carbanion and form a resonance structure. Oops, sorry, I drew it the wrong way. This would come here, and this would come here. So we have a resonance structure where we put the negative charge on a carbon. And then on the right structure, again, we can do resonance with that carbonyl carbon. And we can push that negative charge onto the oxygen. So for these 3 options, the hydrogen on the far left on this carboxylic acid structure, this one is going to be our most acidic hydrogen because for starters, it has a minus charge on a more electronegative atom, but it also can form a resonance structure with another electronegative atom. Between the middle and the group on the right, the group on the far right of the structure is going to be our next most acidic, or in the middle, because our negative charge is on a carbon, but we can resonate with an oxygen, whereas the C minus in the middle, we can only resonate with another carbon. So the group on the right has a better resonance structure because that negative charge ends up on a more electronegative atom, whereas in the middle, it just ends up on another carbon. So the one in the middle would be our least acidic hydrogen. Questions on this one? Okay. You have a question? So they all have resonance, but where that negative charge ends up also affects the stability. So on the far left of the structure, we had an O- resonating with an O-. In the middle, we had a C- resonating with another C-. And then on the far left, we had a C- resonating with an oxygen. So the left side had the more electronegative atoms, the middle had the least electronegative atoms, and the one on the right is going to be in the middle because it had one electronegative and one less electronegative atom. Mhm. Yeah, that's a good question. So a dipole moment kind of thing would you might see something like, I don't know, maybe something like this, where we have the top structure, we have a negative charge, and then next to it is a CH3. The bottom structure, we have it next to a CF3. So fluorines are very electronegative, so they'd be withdrawing electrons by an induction effect. It's not resonance, but because fluorines are so electronegative, they'll kind of just naturally pull electron density towards them. So between these two, the more stable would be the one with the CF3. Again, because the fluorines pull that electron density away from that negative charge, so we're kind of spreading that electron density out throughout the molecule. Yeah. So I'm going to go ahead and move on to question 3. So if you're kind of rusty at the identical structural enantiomer, diastereomer, isomer questions, I suggest you review it. For me, the easiest way I like to go about these ones is, especially if they're 1 or 2 chiral centers, is I like to just assign the R and S for each of the carbons. I'm just going to label them as 1 and 2. So on the left structure, our first carbon, our highest priority is going to go to the oxygen atom. Our lowest priority is going to go to the hydrogen. This CHO group, this is going to be an aldehyde group, so that carbon is double bonded to the oxygen. So for that reason, the top group is going to get our second highest priority because it would be OOH. The group on the bottom would be COH. So the group on the top would be our second highest priority. The group on the bottom would be our third. And then when we do our rotation, we find that this is going to be R. But because our hydrogen is on a wedge, we have to flip that. So this is going to become R. So carbon 1 is, or sorry, S. So carbon 1 was S, and then moving on to carbon 2. Again, oxygen is going to be the highest priority because it's the greatest number on the periodic table. Hydrogen's the least. The group going towards the top is going to get our next highest priority because we have COH, whereas the methyl group at the bottom is just going to be 3 hydrogens. So we have 1, 2, and then at the bottom was 3. So when we do our rotation, we find that this is going to be S. But again, our hydrogen is on the wedge, so we need to flip that. So carbon 2 is going to be R. And then moving on to the structure on the right, our carbon 1, highest priority is going to be ROH. Hydrogen the least. As we determined in the left side, our CHO is going to be our second highest priority. And then towards the bottom is going to be our third. So when we do our rotation, this is going to be R. Again, hydrogen is on the wedge, so we need to flip it. So we'd get S for carbon 1 of the right structure. And then carbon 2, oxygen highest, hydrogen lowest, group towards the top second, and the methyl group towards the bottom is third. We do our rotation, we find that this one is going to be R. Our hydrogen is on a wedge, so we need to flip it. So this one's going to be S as well. So we went from C1S to C1S, and we went from C2R to C2S. And so whenever we have one chiral center stay the same and one chiral center switch, this is going to be diastereomers. Identical would be if the chiral centers for each of those stayed the same. So SS, RR, or SS, SS. Enantiomers would be if they would both switch. So S to R, R to S, or vice versa. And structural would be if the groups that are attached to carbons 1 and 2 were different between the two structures. But again, for this one, we have diastereomers. Questions on this one? Okay, moving on to number 4. Resonance contributors. For this one, we graciously already have the resonance contributors drawn out for us. We're asked to place the contributors in order of the increasing importance. So the number 1 rule for the importance to the hybrid is going to be the octet rule. So the first thing I would do is to make sure that all of these groups have their octet. We can just count the number of electrons around each atom that we're looking at. So for the minus charge on nitrogen on the left, we have 1, 2, 3, 4, 5, 6 with this bond to carbon, and then 7, 8. So the octet rule is satisfied. The minus charge in the middle, we have on a carbon, so we have 1, 2 with the lone pair, 3, 4 with the bond to oxygen, 5, 6 to this hydrogen, and 7, 8 with the bond towards the carbon going to the right. Sorry, this one was a carbon, not an oxygen. So this one has the octet satisfied. And then oxygen, 1, 2, 3, 4, 5, 6, 7, 8. So for all of these, the octet is satisfied. So then the next rule is going to be based on the electronegativity of the atoms. So whenever we have a minus charge, like we do in this question, we want the electronegative, or we want the negative charge to be on a more electronegative atom. So again, electronegativity is going to increase going up and to the right on the periodic table. So we're looking at a carbon, an oxygen, and a nitrogen. So carbon is the least electronegative atom, so this one is going to be our least important to the hybrid. Nitrogen is in between carbon and oxygen, so this one is going to get number 2. And then oxygen is the most electronegative of the 3, so it's going to be our most important to the hybrid. So then for 4b, we're asked to place the hybridization of the nitrogen atom in the box. So hybridization is going to be sp3, sp2, or sp. So whenever we have sp3, we have 4 regions, either bonds or lone pairs. sp2 is going to be 3 regions, and sp is going to be 2 regions. So we're looking at the nitrogen and all of these structures. So whenever you're asked to look at an atom for the resonance contributors, make sure that you look at each of the resonance contributors for the lowest hybridization possible. So if we look, just starting with the left side, we have a lone pair, a bond, and a bond to carbon. So we have 4 regions, and therefore sp3 hybridization. In the middle, we have a lone pair, a bond to carbon, and then a double bond to carbon. So we have 3 regions, which would give us sp2. On the right, again, we have a lone pair, a bond to carbon, and a double bond. So this one is also going to be sp2. So again, you're going to go with the lowest hybridization of the resonance contributors. So our answer in the box is going to be sp2 because that's the lowest of the ones that we have. Questions on this one? So for the plus charge, again, make sure you're looking at your octet rule. If you have a carbocation, carbocations are always, or they never have their octet rule satisfied. They're always electron deficient. So usually if you had a plus charge and you saw it was on a carbon, that one would be the least important to the hybrid. And then again, you'd look at the electronegativity. So you might have maybe a plus charge on an oxygen versus a plus charge on a nitrogen. So it would be the same, but opposite for plus charges. Yep. When we have a plus charge, we want the less electronegative atom to have that plus charge. Okay, I'm going to go ahead and move on. So for this last question on this page, we're asked to look at this cyclohexane. We're asked to find the more stable chair conformation and find the methyl groups that are in an equatorial position. So whenever we want a more stable chair, we are going to draw the biggest group in an equatorial position. So if we look at the structure that we're given, we have a couple of ethyls, we have some methyls, and no other big groups, I guess. So our biggest group is going to be an ethyl. So I'm just going to choose one of these carbons to start with, and then I'll kind of base the rest of the chair conformation on that. So I'm going to start at the bottom as my carbon 1. So I'm putting the ethyl in the equatorial position because it's bigger. CH3 is going to go on the other position. And so from here, I put my wedge in the up position. So all my other wedges will be in the up position on their respective carbons. And then our dash was on the down position. So we're going to put all our other dashes on the down positions at their respective carbons. And then from here, I'm going to go and complete my ring. So we finished carbon 1. I'm going to go up towards the top carbon 2. This one just had some hydrogens. Carbon 3, we had a methyl group in the wedge position, so the up position. Our other group is going to be a hydrogen. Carbon 4, we had an ethyl on the down position. So we have that in the equatorial. Carbon 5, we have a methyl on the down position. And carbon 6, we have an ethyl group in the up position. So whenever you draw your chair conformation, you're going to want to make sure that you did, in fact, draw the more stable chair conformation. And so the reason for this, or the way you can figure this out, is you can see the bigger groups that you have and see which ones are equatorial and which ones are axial. So in the structure that we drew, we have 1, 2 ethyl groups in an equatorial position, and our third big group, or our third ethyl, was on the axial. So if you wanted to, you could draw the ring flip conformation where all your equatorials would become axial and vice versa. For sake of time, you know that if your equatorials become axial and your axials become equatorial, when we flip the chair that we drew specifically, we would have 2 ethyls axial and 1 ethyl equatorial. So if we did that ring flip, this would actually be a less stable conformation because we have more big groups in the axial position. So the one that we drew ended up being the most stable. And so now that we have that most stable chair conformation drawn, we can find what it's asking for. So we're asked to find methyl groups in equatorial positions. So if you look at the structure that we drew, this methyl was equatorial. This one at the bottom was axial. And those were our, oh, sorry, we had this one down here too. So this one was also axial. So we end up only having one methyl group in the equatorial position. So our answer is going to be 1. Questions on this question? Mm-hmm. Sorry? Yeah, so a lot of people like to use down dash just because it's easy to remember. So then if you put all your dashes on the down position, you just, do the opposite for your up positions, which would be equatorial, or sorry, down dash wedge up. You can do that if you want to. The way I do it, I kind of just picked one and went with it. So it kind of just ended up working out, which may or may not be the case on a different problem, but okay. Any questions on any of the first page of facts? Okay, I'm gonna go ahead and move on to our second page of facts. So we have a Grignard question. So we're asked to look at these 2 structures and see if they will produce a useful Grignard reagent. So whenever we need to form a useful Grignard reagent, you'll notice that we have a halide on our structure, so that would then go to form the Mg halide. But we need to make sure that that structure that we have does not have any other reactive functional groups. So those would be acidic hydrogens, so like OH, triple bond, terminal alkynes. Usually like double bonds, so C double bond O, S double bond O, nitro groups. It's not a comprehensive list, so I suggest you go back at the notes and look at the list that she gave you. But you'll notice for the group that we have on the left, we do have one of these double bond oxygen sulfur groups. So this is going to be a reactive functional group. So this one is not going to produce a useful Grignard reagent because the magnesium, it could maybe form some Grignard, but probably a lot of it would go and actually react with that S double bond O, and so that would kind of ruin the reaction that we want to do. So the group on the left is going to be a no. And then if we look at the group on the right, we do have a sulfur group, but it's just single bonded to a couple of carbons. So whenever we have these ether sort of structures, so ether is the oxygen bonded to 2 different carbons. These ones are actually not reactive enough to ruin the Grignard. So this one is actually going to be a yes. It's not reactive enough to ruin our reaction, so it will produce a useful Grignard reagent. Questions on that one? Yes. So if you had a question that was just asking, will this react with a Grignard reagent? It's a very subtle difference, but usually for those questions, if you just want to react with it and not produce a useful Grignard reagent, you might see almost the same thing, except usually there's not going to be a halide, because a halide is usually what we want to do to produce the useful Grignard reagent. So if we saw a question like this at the top, where it's the same thing just without the halide, then our answer would be flipped, because that S double bond O would be a reactive group, so it would react with the magnesium reagent. And then the single bonded sulfur would be a no because it's not reactive enough. So you kind of have to pay attention to the wording of the question. And then again, I like to use what the structure looks like, if it has halides or not, as kind of a hint to the type of question that they're asking. Exam 3 is going to be a good one to kind of look at and do practice with that kind of question. Because exam 3, she asked kind of the same thing, but usually she gives you probably like 5 or 6 different groups to look at. So that one just gives you a lot of practice with these kinds of questions. You mean like this? Something like this? A carbon double bond carbon, so just a C double bond C, that's not reactive enough, so that one would be okay to have in your structure if you wanted to form a useful reagent. The ones you have to watch out for are the terminal alkynes, because they have an acidic hydrogen. Internal alkynes, where they have bonds to carbons on either side. These ones are also okay because they don't have that acidic hydrogen. So C double bond C is okay, and internal alkynes are okay. But usually any other double bond that you see is probably going to be reactive. So again, I can't remember the chapter off the top of my head, but she does actually like list out like a ton of those functional groups that you have to watch out for. Okay, I'm gonna go ahead and move on. Did you have something to say? Okay, yeah, so chapter 10 would be what you want to look for to find those functional groups. So question 7. So we're given an IR spectrum and we're asked to find what the structure is going to look like. So your IR spectrum is going to tell you the functional groups that you have. So like alcohol, carboxylic acid, C double bond O, C double bond C, C triple bond, all that kind of stuff. So James has a very helpful cheat sheet for IR NMR on his website. So I highly suggest you look at that because it is a really good cheat sheet. And it helps practice with identifying what peaks look like and what they tell you about the functional groups. So in this IR spectrum that we have this very broad peak from about like 2300 to almost 3500. So for broad peaks like this, we usually have alcohols or carboxylic acids. The only difference is that the carboxylic acid. The carboxylic acid peak will also overlap with the CH region, which is at about 3000. So you kind of see this broad peak with like a little spike at the end of it. So this is very characteristic of a carboxylic acid. So I know in my structure we're going to have this functional group, so I can go look and see if I can eliminate any of my options. So you'll see A and C have this carboxylic acid group, so we can eliminate B and D. And the reason why these ones are not carboxylic acids, we do have the double bond O and then the OH, but carboxylic acid is specifically this functional group where the C double bond O is attached to the OH. Here we have a couple of carbons in the middle, and this one, it's tricky, but we do have a CH2 in between the alcohol and that carbonyl. So these are not carboxylic acids. So we are going to eliminate them as options. So now the only difference between A and C is we have a double bond in a C double bond C in A. So our C double bond region is going to be in 1600 to 1800. We're going to look here. And so we do see that we have a peak. However, remember that we already know that we have a C double bond O. So we only have one double bond peak in this region, which corresponds to the C double bond O in the carboxylic acid. So we actually do not have a C double bond C in our structure. So no C double bond C. This one just relates to the C double bond O that we already again saw in that carboxylic acid peak. So for that reason, we are going to get rid of A, and C is going to be our answer. Questions on that one? I'm not sure what you mean. So yeah, so 1600 to 1800, you could see C double bond C, C double bond O, usually C double bond N. And so for the purposes of like what we learn in the class, you're not going to see the C double bond N because that's orgo-2 stuff. So your two options pretty much are C double bond C or C double bond O. So it's kind of just practice with using the charts that you're given. You are given this chart on the exam to help you kind of look at the IR and the NMR. But again, I would suggest doing practice beforehand with like Quizlets or James. Again, his cheat sheet is really good. And there's very characteristic regions for each functional group. So I just suggest practicing with that and finding, oh, this is what a carboxylic acid peak looks like. This is what an alcohol peak looks like. Because you can use the chart on the exam, but it kind of takes a lot of time. And you're already kind of pressed for time with only 2 hours. So spending all this time trying to look at the chart and find what you're looking for and, oh, what region is it at? And then going back to the spectrum, it just takes a little bit too much time. So doing some practice beforehand would be really beneficial for the exam. And again, James' cheat sheet, like it's really, really good. So I'm going to go ahead and move on. Number 8, I also suggest doing a lot of practice with these kinds of questions. So in this question, we're asked to find signals. We're asked for a few proton NMRs of this compound. So number of signals is basically just going to be the number of different hydrogen peaks that we have. So I'm just going to start from the left and go to the right. So we have this double bond here on the left of the structure. So we have this hydrogen here. So I'm just going to label this as 1. We do have another hydrogen attached to the same carbon, but whenever we have a double bond, we need to take consideration of the stereochemistry. So on the top, this hydrogen is adjacent to that big chain, the rest of the molecule. On the bottom, this hydrogen is directly next to another hydrogen. So in a double bond, the splitting pattern is actually going to be, or could be different between hydrogens of the same carbon because of the stereochemistry and the double bond not being able to rotate. If the bond could rotate, then we wouldn't need to consider the stereochemistry, but that bond is locked in place, so you're always going to have that specific interaction between the top and the bottom, which affects your splitting and affects your signals. So again, the hydrogen on the top was next to the CH group on the right. The hydrogen on the bottom is next to a hydrogen. So on the left, these two hydrogens are actually going to give different signals. So then moving on to the next carbon, this one's obviously different from the previous two, so I'm going to number that one as 3. Then we're moving on. We have this CH right here. Again, this one is obviously different in connectivity. Going across, this hydrogen is different in connectivity. And you'll consider hydrogens on the same carbon as 1, except for double bonds, as I mentioned earlier. Then we have another CH with a couple of ethyls coming off of it. So this is going to be 6. Because we have 2 ethyl groups coming off of that same carbon, these 2 peaks are actually going to be the same. because the connectivity is the same. So the CH2s of those ethyl groups are both going to be giving us the same signal. So we're going to number that as 7. The CH3 would give us a different signal, which would be 8. But both of the CH3s would be that same signal. So those will both be 8. And then we have this OH, which is obviously different as well. So that's going to be number 9. So we have 9 different hydrogen signals. So we're just going to put 9 in our box over here. Okay, for 2, we're asked to look at the multiplicity of HA. So HA is right here. So again, or I guess I should say for proton NMR, we are going to look at neighboring hydrogens. And remember, we're going to look at the n+1 rule. So each different neighbor is going to be an n+1. And then if you have multiple different neighbors, you're going to have each of those multiplied together. So looking towards the left, we have the CH2 on the end of that double bond. And again, because it's in that double bond, we do have to consider these hydrogens as separate signals. So up top, we have 1 hydrogen, so that's 1 + 1. Bottom, we have 1 hydrogen, 1 + 1. And then looking at our neighbor to the right, this one also has a hydrogen. So this will also give us a 1 + 1. So in total for HA, we have 1 + 1 times 1 + 1 times 1 + 1. So that's going to give us 2 times 2 times 2, which is going to be 8. So that's the number that we'll put in the box. Going on to HB. So this is the hydrogen that we're looking at. Our neighbor to the left, we have CH2. So our N is going to be 2 and then +1. Looking up top, we have a CH2, which was at the signal we numbered 7. And then you'll notice that we have 2 signals labeled as 7. So we have a CH2 up top, CH2 to the right. So this one, because those signals are going to be the same, we're going to add the hydrogens together. So we're going to get 2 + 2 and then again +1. So this is going to give us 3 times 5, which would give us 15. For HC, we're looking at these hydrogens on the end of this chain. The only neighbor that we have is going to the left, which is going to be the CH2. So our N is going to be 2 + 1, and that's going to give us 3. Okay, then we're looking at HD, which is on this alcohol. So we're looking at this hydrogen. Our neighbor is going to be this CH group. So we have 1 neighbor. And so that's going to give us 2. I want to point out that the only time that you will consider the signals for an OH, an NH, or an SH is going to be when we have ultra pure conditions like it is specified in the instructions. So normally these hydrogens are too acidic to the point where they'll be protonating and deprotonating too fast for the machine to pick up the splitting pattern. But under ultra pure conditions, this allows us to see that splitting pattern. So again, under ultra pure conditions, you'll kind of just treat it like normal. But if it was under maybe not ultra pure conditions, you might have to look at something different. But I highly doubt, I don't even think she would put non-ultra pure conditions on the exam. Yes, I would think so. Because again, like I just don't think it would be picked up by the instrument. So then kind of it would just be like blank, like you wouldn't see it there. 8, yeah, 8 signals, and then for HD, I mean, yeah, I think you'd have to be asking about like this one right here that's attached to the OH, so you wouldn't see the OH one, but then you'd consider like the other ones. But in all the exams I've ever seen, she only puts ultra pure conditions. But do make sure you're reading your instructions because who knows? Do you mean like with the ethyl groups that we have? So yeah, so I think you're asking why um these two like they're the same because of the connectivity, but we still add hydrogens together. Um, so they are the same connectivity, but you do have those groups. So the proton NMR is picking up the signals from the hydrogens in that structure. So because those ethyl groups both exist, we would still see a signal for that. It would just kind of stack on the same signal because the connectivity is the same, if that makes sense. Yeah. I'm gonna go ahead and move on for sake of time. So getting into the reactions, make sure you go back and again review your exam 2 stuff with your elimination and substitution, because that will definitely come back on this exam. This first question, we have NBS and light, which remember is the allylic bromination, where our first step is we add a radical to the position next to the double bond. So in this structure, we could add a radical to the group or the side going to the left. We cannot add a radical to the side going to the right because it already is bonded to 4 atoms. So this already has an octet. And so if we added a radical to that, then there'd be more than 8 electrons at that carbon. So that's not possible. So then after we find our radical position, the next step is to just add our bromine at that position. So we just add our bromine where we put our radical. And you'll notice that there's 2 boxes. So remember that anytime we form a radical, we can also do resonance. So our second structure is going to come from the resonance that we can do with that radical. So then we form a radical kind of at the bottom of that chain there. So our second structure would be with our double bond in the new position and our bromine coming off of that other carbon. So number 2, we have an alcohol, and then we have elemental. Anytime you see that like O superscript, that's going to be elemental, in this case, potassium. So whenever we have elemental potassium, or you could see sodium, so the first group metals, this is going to remove the OH, or sorry, it's going to remove the H from the OH. So all we're going to do for reaction 1 is we're going to form an O-. So reaction 2, we have an O- and we have a secondary halide. So remember, O- is going to be a strong base. And we have a secondary halide, so this is going to do an E2 reaction. Make sure you brush up on like your flowchart or whatever you use to kind of determine SN1, SN2, E1, E2, because she could have given us a primary halide and then we would have done SN2. In this case, since it's secondary, we'll do E2. So we have a strong base, and because we have all of these groups coming off of this carbon here, it's also going to be bulky. So when we do our elimination product, we're going to want to form the less substituted alkene. So we're just going to, in this case, the bromine would get kicked out as the oxygen takes a hydrogen. And we want to form, again, the less substituted alkene. So we're going to form this structure here. So then step 3, we have Br2 and H2O. So this one adds OH and bromine, and the OH adds to the more subbed position. So we have our OH, and then our bromine is going to go on the other carbon. Going on to the last reaction of this page. Stereo? Oh, no, I don't think you need to. You would form, yeah, you'd form the same alcohol, but this is the one that we'll react with, so that's the one that you have to draw. If you drew the other one, though, you wouldn't get points off unless you use that to do the next reaction. But good question. So for number 3, we have CH3O-. Again, O- is going to be a strong base. We have, in this case, a tertiary halide. So again, we're going to do an elimination reaction. So remember, for E2, we need the hydrogen in the halide to be either transdiaxial for a cyclic structure or anticoplanar for a linear structure. So basically that just means we want our hydrogen and our bromine to be kind of on opposite sides, so one up, one down, or vice versa. In the structure that we're given, you'll see that we have the syn conformation where they're on the same side. So before we can react, we need to rotate our structure, which will affect the stereochemistry of the final product. So I'm just going to draw my hydrogen on the up position. I'm going to rotate just the left side, so the right side will stay the same. And then our groups on the left will be switched. So our benzene will end up on the top and our CH3 on the bottom. And so now we can do our elimination reaction. And you wouldn't have to draw this step out, but if you wanted to kind of use it to visualize, that's okay. So then the strong base will do the elimination. So we're just going to form a double bond in that position. So we had our 2 benzenes are on the same side, and our methyl groups were on the same side on the bottom. So step 2, we have CHCl3KOH. So this one, it's similar to, I like Hamza's name for it, the Illuminati reaction. It's not the Illuminati reaction, but it's sort of like the Illuminati reaction. So this one, we form the triangle with the chlorines in the double bond position. We have our carbons that were in the double bond, and then we have our chlorines. And then we just had our other groups, and the stereochemistry will stay the same. Yeah, that's fine too. As long as the important part is the benzenes and the methyls. Any questions on this first page of reactions? I don't know. I mean, I feel like I've seen on some keys where they kind of just draw it out as the lines, but at the same time, let's say like a TA marked your points off for that, and then you wanted to try and get it regraded. You might not have a very strong argument to stand on because you didn't draw the stereochemistry out. So I would just suggest getting in the habit of drawing the stereochemistry to kind of protect yourself from the grading. Mhm. Yes, yeah. So transdiaxial for the cyclic structure. So that's kind of like when we looked at the chair conformation. So we made something like this. For the linear structure, like we have here, it's the same concept. It's just called anticoplanar. So we need the hydrogen to be up and the bromine down, or vice versa. I'm sorry? Oh yeah, yeah. No. On the key, there's no stereo drawn, but if you drew it, it wouldn't be counted off. I don't think. I think that one does anti-addition. So moving on to the next page. So we have H3O plus and we have a double bond. So H3O plus with a double bond, the first step is going to be the addition of a hydrogen to the less subbed side of the double bond. So we'd add our hydrogen here. And then since the other side did not gain that hydrogen, it's now going to be our plus charge. So this one forms the planar carbocation, because that carbocation is sp2. So the next step of the H3O plus reaction is we will react the H2O then with that carbocation. And this one specifically is just going to be the SN1 product. You'll notice that we have two boxes here. And so because we have this planar carbon, we're going to draw both the stereochemistry products for this reaction. So SN1, remember, does the 50-50 mixture. So 50% of our product would be the R, and then the other 50% would be the S. So just for the purposes of the exam, you'll just draw one of them where the OH ends up on the dash, and then the other one, the OH on the wedge. And those would be our two products. Going on to reaction 5, we have KOH with a dihalide structure. So this one's going to form the internal alkyne. So step 1, we're going to form our 4-carbon alkyne with the triple bond, in the middle. Steps 2 and 3 are coupled together, so we'll show them in the same step. And this one does an addition of OH and H anti-mark. And then this one also does the tautomerization, and our end product is going to be a carbonyl, so like a C double bond O. In this case, the structure is symmetrical, and there's not a difference between the two carbons in the triple bond, so you could draw the carbonyl on either side of that triple bond. So we're going to end up with this ketone. And then step 4, this is the Raney nickel reaction. And this one reduces pretty much anything you could think of. And it's going to turn the double bond O into an alcohol. So our end product is going to be the alcohol. Reaction number 6, we have osmium tetroxide, H2O2, and OH. So this one was on the synthesis of exam 3. So this one forms the syn diol. So we're going to add a OH to both carbons in the double bond, and they're going to be on the same stereochemistry, so both on wedges or both on dashes. Our next step is a new reaction. This one's the periodic acid cleavage. And so this one splits the molecule between the two alcohols, and then it will turn the alcohols to ketones or aldehydes. So because the alcohols we have, the carbons have 2 other carbon groups on them, we're going to form a ketone. And you'll see if we split the molecule, it's going to be symmetric, so you only have to draw one, you don't have to draw both. So then step 3, we have the acetylide anion. We have this carbonyl group. So the C- is going to come in and attack at that carbonyl, and it's going to kick the double bond oxygen to be an O-, and then our H3O+ will protonate that O- to form the alcohol. So this one is just one of the carbon-carbon bond forming reactions. And then step 4, we have H2-PDBASO4 and quinoline. So this one's Lindlar's catalyst. And so this one forms the cis double bond. The PDBASO4 prevents it from going all the way to the alkane. And we have to show the stereochemistry as well. So the rest of our group will be the same. I'm going to draw the hydrogens on the same side of that double bond. Any questions on this page? Okay, and go ahead and move on. Our next reaction, we have H2SO4 and heat. So remember, this one is an alcohol dehydration. And this one forms, ideally, the more substituted alkene. So we have this primary alcohol here. And so even though this alcohol is on a primary carbon, this one does rearrange, again, to form the more subbed alkene. So our options to form the double bond are going to be here, here, or here. So the major is going to be, again, the more substituted alkene, and that in this case is going to be going to the left because that would give us a tetrasubbed alkene. And then our 2 minor products are just going to be the other 2. So going to the right, up and to the right, we have a trisub. And if we went towards the bottom, we would have a disub. So the tetrasub product will be our major, and then the other 2 will be in our 2 minor boxes. Number 8, we have KMNO4 warm concentrated. So this is going to be the double bond cleavage. And it also oxidizes the carbons that were in the double bond. So because we had hydrogens attached to each of those, this one is going to form ketones or carboxylic acids. And because we have the hydrogens, these hydrogens will be oxidized to form the carboxylic acid product. So step 1, we're going to form our carboxylic acid. Step 2, we have CH3OH and H+. So this one is also new, and this one forms esters. And so esters are going to be whenever we have a C double bond O, an O, and then another carbon. That's what an ester looks like. And so the carbon group that we attach to the right side of that carboxylic acid is going to be whatever the alkyl part is from the alcohol. We had the O, and then in this case, we're going to add a CH3. Then step 3, we have a Grignard reaction. Whenever we have a Grignard reaction with an ester like this or with an acyl chloride, we're going to add 2 equivalents of the Grignard to the carbonyl, and the ester part or the acyl part gets kicked out, and like normal, our double bonded oxygen will become the alcohol. Our double bonded oxygen becomes the alcohol, and then we're adding 2 of our Grignards, which are going to be the hexane. For our last question, it's kind of 2 questions in one. So going to the right, we have a PBr3. Going to the bottom, we have the tosyl chloride. I'm just going to start with the top. So remember that PBr3, we replaced the OH with bromine. And this one is SN2-like. So we're going to flip the stereo. So we went from the oxygen being, or sorry, the OH being on the wedge. So now our hydrogen will be on the wedge, and our bromine will be on the dash. And then step 2, we have CH3S-. So we have a weak base and strong nucleophile because it's negatively charged. So this one's going to do an SN2 reaction. And again, SN2 flips the stereo. So the end product of this reaction will have the hydrogen back on the dash and our SN2 nucleophile on the wedge. So going down, we have the tosyl chloride reagent. And so this one, we are going to form the OTOS. And this one retains the stereochemistry. So our hydrogen stays on the dash, our OH becomes OTOS, and it remains on the wedge. And then step 2, it's the same reagent as the group going to the right. So this one, again, is going to be an SN2 reaction. So this time, we will flip the stereo. So our hydrogen is going to be on the wedge, and our CH3S will be on the dash. So these are kind of 2 ways that you can do like an SN2 reaction to get different stereochemistry products. Any questions on the reaction section? Okay, I'm going to go ahead. Yeah. It'll make an aldehyde if one of the if there's a terminal alkyne. So if we had something like this, but because in this case both of our carbons, it's a symmetrical molecule and both of them are internal, we just form the ketone. So that's a good question. I'm going to move on to mechanism. So for this mechanism question, you'll see that we form kind of like a substitution reaction, and then our other one we do a ring expansion and we form a ketone. So the first step of this reaction, we have a secondary halide, we have a weak nucleophile and a weak base. So this one is going to be SN1-like, and for SN1 reactions, our leaving group just leaves for the first step. So for the first step, we're going to have essentially the same structure, except we're going to have a carbocation at the position where the bromine was. Our OH will be there. So from here, A is a pretty easy one to go for. We just have to do, again, the substitution part of the SN1 reaction. So we're going to have our CH3OH, our nucleophile. It's going to come in and attack at that plus charge. We'll have a bond to OCH3, and then don't forget your hydrogen still attached. And then for the last step of this mechanism, we just have to show that hydrogen being deprotonated from that O+. So we formed A. That was not too bad. For B, product B, we have to do a ring expansion. So I'm going to start from here. I'm just going to number arbitrarily to keep track of my ring. Make sure I form everything in the right spot. So kind of in my work, carbon 3 ends up being the carbon with the oxygen. I'm going to number down around the ring. And again, this is arbitrary. You could have started from somewhere else, wherever makes sense to you. Again, this is just to keep track of making sure I'm putting everything in the right place. So you'll see in the end product, we formed a bond between 2 and 7. So I'm going to show this bond right here coming in and attacking carbocation. So this would be a bond shift. So then, product of that, we are going to have a 6-carbon ring now. This one will be attached to the cyclopentane. This was carbon 2, this was 7, this was 1. So now carbon 3 is going to have my OH. And because we lost that bond between 3 and 7, 3 is going to have our new plus charge. And so from here, we can form a resonance structure with this OH. So OH is going to donate one of its lone pairs. Now we're going to have this double bond OH. It's going to be our new plus charge. So then from here, in order to form product B, we just have to again deprotonate that oxygen. So you could use Br or you could use CH3OH as your nucleophile. You just have to show the nucleophile taking that hydrogen and that hydrogen donating its bond back to oxygen. So that's the mechanism. Any questions on this one? The extra hydrogen? Which step are you talking about? This one? This one? So in that step, the CH3OH is our nucleophile. So that whole molecule is going to attack, and then it still has that hydrogen on it. So the last step, we just have to show that it's deprotonated. And then it's kind of the same thing for the other half of the mechanism. And we just do the bond shift, we do a resonance structure, and then we just have to deprotonate that oxygen to form the neutral oxygen. I'm gonna go ahead and move on to synthesis. So for synthesis, we have an ester. Again, our ester is going to be whenever we have the C double bond O to an OR. So another carbon on the other side of the oxygen. So whenever we have this ester, what we're going to want to do is the ester formation reaction, but in reverse. And so that is going to be the reaction of a carboxylic acid with an alcohol. So the single bonded oxygen part is going to become your alcohol, and the double bonded oxygen part is going to become your carboxylic acid. So for this one, I'm going to split in between the double bond O and the single bond O. Over the arrow is going to be H+. So then our alcohol part will be this long chain here, OH. And then our carboxylic acid part will be the part at the top. And so then from here, we're going to want to ideally get back to alcohols to do Grignard with. We're allowed to start with alcohols of 5 carbons or less, and only alcohols. So no alkenes, no alkynes, no, not even a cyclohexanol. So I'm just going to work back the left side since it's already in the alcohol form. So we're just going to do a Grignard. We're going to split there. That's going to give us a 1, 2, 3, 4 carbon piece and a 1, 2, 3 carbon piece. So we're going to have then H3O plus over the arrow. Our alcohol part is going to be the carbonyl. And the other part is going to be our Grignard. We can work this aldehyde back to a 4-carbon alcohol using PCC. And so we're allowed to start with 5-carbon alcohol or less, so this one is good to go. On the other side, we're going to do our Mg ether. That's going to turn that back into the bromine. And then we have a primary halide, so we can do the PBr3 reaction to turn this back into the alcohol. And this is a 3-carbon alcohol, so we are good to go. On the other side, we have a carboxylic acid. So whenever we want to form a carboxylic acid, we're going to use one of our strong oxidizers. Jones is the easiest to write out, but you could also do the Na2Cr2O7 reagent. And that's going to turn that carboxylic acid back to a primary alcohol. So this is 1 carbon too long. So we will have to do another Grignard. I'm just going to split here, because that would give us a 5-carbon piece and a 1-carbon piece. So for Grignard, again, then H3O plus over the arrow. Our double bond part will be a single bonded, a single carbon aldehyde. We can work that back with PCC to form methanol. And the other half was the 5-carbon piece, which is going to be our Grignard. We have MgBr. We're going to do Mg ether to turn that back into the halide. And this is a secondary halide, so we can still do PBr3. And that will give us a 5-carbon alcohol. Questions on this? Excess is only going to be for a bromination reaction with an alkane. So if you wanted to do like cyclohexane to bromine, then you'll do excess. other questions on synthesis? Okay, we can go ahead and move on to our last section, spectroscopy. Again, start practicing this one early if you haven't already, because this one does take kind of some practice. It's kind of like a puzzle, so building up your brain strength will help you out. The first thing that you're going to do for spectroscopy is you're going to calculate your unsaturation number, and that's going to tell you how many double bonds or rings that double bonds, triple bonds, or rings that you have in the structure. Formula is going to be 2 times carbon plus 2 minus the number of hydrogens all over 2. In this case, we have 10 carbons plus 2 minus 12 hydrogens all over 2. So that's going to give us 20 plus 2, which is 22, minus 12, which is 10 over 2. So we're going to have 5 unsaturations. I always suggest, especially for the first time you have spectroscopy, to calculate your unsat and then do it again, just to make sure you didn't make any silly math mistakes, because I did it plenty of times when I was taking the test. And again, James's cheat sheet or just any online resources to kind of help you identify characteristic peaks of the IR NMR spectrum is going to be very helpful. In the IR that we have, IR is going to tell us functional groups. So we do not have a broad OH peak here. So we know that we don't have an OH. The 21 to 2300 would be our triple bond region. We don't see anything here, so there's not going to be a triple bond. Our 16 to 1800 is going to be our double bond region. And we do see a couple of peaks here. So our unsaturations are going to come from either rings or double bonds. And this could be C double bond C or C double bond O for the double bonds. So the next thing I like to do is I like to try and see if there's going to be a benzene in my structure. So benzene is a ring that has 3 double bonds in it. So each ring and each double bond contributes 1 unsaturation number. So in total, we'd have 1 unsat from the ring, and we'd have 3 unsats from the double bonds. So benzene would give us 4 unsaturation numbers. So we have 5 total, so that means it's probably pretty likely that we will have a benzene in our structure. And the way you can confirm this is by looking at the 6.5 to 8-ish region. I think it's like 6.5 to maybe 8.5 or 9. And this is going to be the benzene region. Again, you will have this chart on your exam, but again, relying on this entirely for your exam, especially if you don't do any practice at all, you're not going to have a good time, because you'd have to look through all of these things and find your peak and then see where it is and then go back and see where it is. So it just takes a lot of time that you don't really have to spare. So again, practice with this kind of stuff. But in our benzene region, we do see some peaks there, so we know that we're going to have a benzene in our structure. And I like to get that out of the way first because benzene is 6 carbons. So we have, what was it, 10 total? So we're already knocking out 6 of our 10 carbons. That's over half of our structure. And then the next thing I like to do with the benzene is to determine the substitution of it. So like where any functional groups would go on the benzene. And so to find the substitution, you're going to add up the total hydrogens you have in that region. So in this case, we have 4. We have 2 and 2. We have 4 total hydrogens on our benzene. And you can put those around the ring, and we'll know that we have 2 substituents. We could have something like this, or we could have something like this. And then the splitting pattern of the benzene peaks is going to tell us where our substituents will be. In this case, we have a doublet-doublet structure. So we have 2 hydrogens, that's a doublet. We have another peak that's 2 hydrogens and a doublet. So anytime you see this doublet-doublet pattern, we are going to have a pair substituted or substitutions directly across from each other. We're going to have this substitution pattern. So X and Y would just be whatever substituents, and they're going to be directly across on the ring from each other. And so the reason for that is the plane of symmetry creates that kind of even looking doublet-doublet pattern. So that's like the telltale sign of that benzene substitution. So far we've gotten a benzene that has its substituents directly across from one another. So now we just have to go through the rest of the structure, the rest of the proton and carbon 13 NMR to find the rest of our carbons. So we know that we're going to have 10 carbons, 12 hydrogens, and 2 oxygens. So we already noted that we don't have an OH peak and we do not have carboxylic acid peak as well. So we know that we don't have either of those functional groups. Another functional group for oxygen that you could look for is an aldehyde. So aldehyde is going to show a characteristic peak on the proton NMR in the 9 to 10 region. So from here to here. And again, we do see a peak in this region. So we know that this one hydrogen here is going to be part of an aldehyde. So for collecting our puzzle pieces down here, we have this para-substituted benzene and we have an aldehyde. This aldehyde will contribute 1 unsaturation number. So now total we have 1, 2, 3, 4, 5 unsaturation numbers. So we've used up all our unsats, so we don't have any more double bonds or rings. We know we don't have an OH, we know we don't have a carboxylic acid, and we can't have another ketone or aldehyde. So we have this one remaining oxygen that we don't really know what it's going to be. So I like to try and find this one last, kind of as a process of elimination. So based on all the other information I have, I know that this oxygen is going to have to be an ether. So it's not an OH, it's not a double bonded O, it's not a carboxylic acid, but we do have another oxygen that we need to consider. So we're going to have an ether. So far on the Proton NMR, we've already checked off this peak. We've checked off these peaks as our benzenes. And then we just have to figure out the last 3 peaks that we have. So we have this 2H peak. And so the number above the peak is going to be the number of hydrogens that carbon has. That's going to be the integration number. So this peak kind of in the middle is going to be a CH2. And the splitting pattern is 1, 2, 3, triplet. So our neighbor is going to have 2 hydrogens of its own. So I like to put what I know in the box and what I'm kind of speculating or guessing about outside of the box. So I know that I have a CH2. I think there's going to be a CH2 attached to it. And then that leaves the other side a mystery. I know it's not going to have any hydrogens of its own, so I'm just going to draw kind of a dot as a placeholder. The next peak we have is another 2H, so another CH2. And you'll notice that this one has a pretty large splitting pattern. You have like 1, 2, 3, 4, 5, kind of like 6 visible peaks there. So whenever you see a large splitting pattern like this, so basically more than a triplet or a quartet, so 3 or 4 peaks, I like to just put this one as M and move on. This usually means that there's going to be different neighbors on either side that multiply that pattern to be kind of unreadable. And then our last peak is going to be this 3H. So we have a CH3. CH3 can only have 1 other bond. The splitting pattern is 1, 2, CH3. So again, our neighbor is going to have 2 hydrogens. And have the CH2, CH3. And so these are all my puzzle pieces. I'm just going to put them down here again for clarity. So we have this benzene, we have an aldehyde, we have an ether, we have a CH2, CH3. Sorry, there's a CH2, CH2. Then we had a CH2 with kind of 2 neighbors next to it. And we had a CH3 with a CH2 next to it. So I put these in this order for a reason. So if I look at the puzzle pieces that I have, and I overlap them, I can kind of see that this kind of looks like it might go together. It's kind of like Legos. You like put the Legos together. So I think that these 3 groups are going to form one puzzle piece, which is going to be this CH2, CH2, CH3. So again, we have the CH3 that had a CH2 next to it. This CH2 had a lot of different hydrogen neighbors, which would make sense with this splitting pattern. If we calculated it, we'd have 2 + 1 times 3 + 1, which would give us 12 lines. So we have a large splitting pattern for that middle one. And then we had a CH2 that had a CH2 next to it and nothing on the other side. So this is going to be kind of my puzzle piece that I put together. So now if I look at the formula and I calculate all the atoms that I have here, our carbons, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've gotten rid of all my carbons. I have 1 hydrogen, 2 hydrogens, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've used up all my hydrogens. And then I've used up an oxygen here and an oxygen here. So I've used up all my atoms. And so the last part is just to put everything together. So I'm just going to put my benzene in first. I know that's going to be kind of my central piece. We have this aldehyde. So we know an aldehyde has to go on the end of a chain. If we were to put this aldehyde on the end of the CH2, CH2, CH3, we just have a 4-carbon chain, and then we wouldn't have anywhere else to put the other pieces. So I know that this aldehyde is probably going to have to be one of the substituents on the benzene. And then I do have this CH2, CH2, CH3, but I also have this last oxygen that I need to put in my structure somewhere. So I'm going to attach it to this half of my structure as that ether. Again, that would match with the splitting pattern we have for that CH2. We had a CH2 on one side and something without any hydrogens on the other. So that would check out. And if you wanted to, you could also look at the Proton NMR for that peak. You'll see that it's very far downfield or to the left. And so the more downfield something is, the more electronegative it's going to be, or the more electronegative the atom it's attached to is going to be. So an oxygen is a very electronegative atom, so it makes sense that that peak specifically is attached to the oxygen. And then carbon-13 NMR, I kind of just use that as a last double check. There's a few characteristic peaks that you can find out from the chart. So for example, this one, if you looked at your chart, would be your aldehyde peak. You would see like maybe this one would be like your ether or something like that. But you don't necessarily need the carbon-13 NMR. It's kind of like a double check. At least that's the way I used it. So that's going to be the spectroscopy. It's kind of a process. So again, I recommend practicing a lot. But other than that, we're done for today. So you are free to go. So the first oxygen was here in the aldehyde. The second one is right there as the ether. So the first one I already saw from this peak right here, which was an aldehyde specific peak. And then the other one was kind of a process of elimination. I know that we don't have an alcohol from the IR, we don't have a carboxylic acid, and we had already used up all of our unsaturation numbers, so we couldn't use it as a C double bond O. And then I saw that this peak here was very far to the left, so I kind of thought, okay, maybe that's going to be an ether where it's just single bonded to carbons on either side. The ether, you mean? So again, I know that we have two oxygens in our structure from the formula that we're given. One of them was the aldehyde. And then we didn't see any other characteristic peaks in the IR. So no alcohol, no carboxylic acid. And we had already used up all of our unsaturation numbers with 4 from the benzene. And the fifth one from the double bond in the aldehyde. So I know that the last oxygen can't be double bonded to anything, because we would have to have another unsaturation number. So I used that one as a process of elimination, kind of like last thing to look at. And I just kind of confirmed it with the peak that's at about 4. So if it's further to the left, so a higher number on the proton NMR spectrum, it's going to be attached to something that's more electronegative. So this peak, it's very far to the left. Usually regular alkyl peaks, like these ones over here, usually they're just like 1 to like 2.3 or something like that. But this one's really far down at 4. So I know it's probably going to be it's probably going to be bonded either to, it could be bonded to like a C double bond O, or like a benzene, or an oxygen. So I kind of use that as like the last step and put it in on the last piece.